Bismillah ar-Rahman ar-Rahim. This lecture we continue the arithmetic circuits. Okay, last time we finished the ripple carry adder, which is composed of full adder cells, okay, that are connected iteratively in a cascading manner, okay, cascaded manner, in which the carry out of one full adder will ripple to the next or will be connected to or will feed the next full adder, okay, and so on and so forth. This topic, which is the magnitude comparator. So what do we mean by magnitude comparator? Okay, let me draw the circuit for you, or draw not the circuit, I mean draw a black box of what do we mean by a magnitude comparator. First of all, as a specification, it takes two inputs, A and B, okay? And A is, we can say it is in bit, okay? In bit, and B is in bit as well. However, for the sake of concreteness, okay, and simplicity, and without loss of generality, we can say that A is 4-bit, okay, which is A3, A2, A1, A0, all right? And then B is B3, B2, B1, B0. So these are the bits of the binary number A. A is 4-bit binary number, okay, and it is unsigned as well. So there is no sign information here, so it is always positive. And the most significant bit is A3, and the least significant bit is A0, okay? And B is also a 4-bit unsigned number, where the most significant bit is B3, and the least significant bit is B0. An example would be, for example, 1 0 1 0, okay, for A, and for B is 0 1 1 0, okay? So these are examples. So if I ask you now, what is A2? Is it a 0 or a 1? What do you say? A2 is a 0, okay? So this is A3. This in this example, A3 is 1, A2 is 0, A1 is 1, A0 is 0, okay? All right, may I ask you now, what is B1?
1.
For this example, what is the value of B1?
It's 1.
1.
1, excellent, okay? So 1. So we have a binary number as input, okay? And another binary number as input, okay? 4-bit, both of them are 4-bit. So this is the input of the circuit, and the output, so this is input, so this is a specification, okay? Input and output, for output. So what is the size of the input? It's 2 4-bit integers, and both are unsigned, both unsigned, okay? We will learn about signed numbers later, okay? And the output of the magnitude comparator will be only 3-bit output, 3-bit, and each bit of the 3-bit will tell us something about the relationship between A and B. One output will be a GT, okay, which will tell us it is going to be a 1. Let me just say that it's going to be a 1 if and only if A as a binary number is greater than B, okay, and it is 0 otherwise. So it is a GT greater than, it's short for greater than, okay, GT, all right? And then we have equal, okay, which is going to be 1. Who can tell me when? If and only if A is equal to B, right? And 0 otherwise. All right, and then we have the third output, which is LT. And LT is going to be 1 if and only if what? A is
less than
Less
B.
than, yeah, excellent. Less than B, and 0 otherwise. So now we have specified our module, which is a magnitude comparator, okay, and we can draw a black box like this, a big black box that takes A and B, and from outside we take, this is a 4-bit number, we know that this is a 4-bit number, and this is how to indicate that. This line here, it has a width of 4, okay, and this line here has a width of 4 as well, and this is the external A signal, and this is the external B signal, okay, and this is called a magnitude comparator. Okay, and we have 3 signals at the output: GT, EQ, and LT. Okay, this is GT, and this is EQ, and this is LT. All right. Now, so if we don't specify any width for the output, it is 1 by default. The output, this wire here is 1 bit, and this wire here is 1 bit, and this wire here is 1 bit. So unless we specify the width, it's going to be of width 1 bit. Okay. All right. So there is some circuit here that takes A and B and produce for us these 3 signals. Okay. Let me test your knowledge about comparison. Okay. So one of the things that you should know is that exactly one of these 3 signals will be 1. Okay. Do you agree with that, or you don't? Is it possible that, for example, none of them will be 1, or 2 of them will be 1 and the third one will be 0? Is it possible? So let's say for the sake of discussion that GT is 1, for example, GT is 1, and EQ is 1. What are we saying here?
This is impossible.
It is impossible. Excellent. Why? Because here we are saying that A is greater than, strictly greater than B. And we are saying also that and A equal to B. And this statement here is false. We know that is a false statement. Okay, it cannot, A cannot be at the same time greater than B and equal to B. It cannot. Okay, but this is, do not confuse this with A is greater than or equal to B. What is the difference here? This is possible. This one is possible. What is the difference? Difference, the keyword is here and here it is or. Okay, so when you replace this and with or, then things can be possible. Okay, you're saying that A may be greater than B or equal to B. Okay, but not both, of course. Okay, so you can say that this is an XOR. Okay, it's an XOR. It's not. So if you think about it, mathematically speaking, or using a digital design, it's an XOR thing. Okay, because logically it cannot be the case that A is greater than B and at the same time equal to B. Okay, so this is an XOR. Anyway, this is a side discussion. And I want you to know that exactly one signal will be 1 at any point of time. Okay, so from what we learned from the design procedure, okay, what is the next step? So now I have specified the problem, right? This is a specification step. What is the next step? It is the formulation step, right? The formulation step, isn't it? What do we mean by formulation? Let me remind you. Formulation means deriving the truth table. Formulation means deriving the truth table. Who can tell me what is the size of the truth table in this problem? Anyone? What is the size of the truth table in this problem? How many inputs do we have?
2 inputs.
8.
Not 2, actually. No, we need to know the
Okay.
number of bits.
Yes.
8.
Okay.
So it is for this example, it is what?
8.
8 inputs. So how many cells or how many rows in the truth table do we have?
8.
8? Only 8? Yes, it is 2 to the 8. Excellent, Ahmed. Okay, so it is 2 to the 8. Yeah, 2 to the 8 means 256 rows. Are you willing to write 256 rows? And each row is how many columns? It's 8 plus 3, which is 11 columns. So 11 times 256 cells, okay, that or zeros and ones that you're going to write. This is too much, right? It's too much. So we have to think at a higher level to solve this problem. Solving it by truth table is not going to work. And also, after you finish the truth table, you're going to do a K-map, which means 8 variables K-map, and we haven't even seen how this looks like. I mean, it's ugly, okay? So let's go back to the page here and see how we tackle this problem, okay? So as I said, the input size is 8-bit and the truth table is 256 rows. So we seek another way. We use logic to basically derive this, derive the output here, okay? So for equality, for example, for equality, we know that A equals B from logic, from your programming courses. Okay, if and only if every bit of A is equal to the corresponding bit of B. And so if and only if A sub I equals B sub I for all I, in our case, I goes from 0 to 3, okay? We have 4-bit, okay? This is without loss of generality. If you have n bit, then I goes from 0 to n minus 1, okay? So this is the equality equation for, so just by giving you this, by the way, I have given you a Boolean function for equality. Okay, you should be able to derive the Boolean function. What is the operation that tests for equality? We have learned an operation that tests for equality. Let me test your readiness for the exam. What is the operation that tests for equality of bits?
XNOR.
XNOR, excellent. So if we say AI equals BI, then we can replace this with an XNOR gate, okay? So that it XNORs AI with BI, okay? So let me just do this here. Okay, so we can say that equal is going to be, or first of all, let's define an E sub I signal, which is bit I equals bit I of A equals bit I of B. Okay, so this signal can be simply the XNOR of AI XNORed with BI. Okay, yeah. So if this is 1, then we know that bit number I is equal to of A is equal to bit number I of B, right? And for equality of A and B for the 4 bits, we need to know that E3 are equal, bit number 3 is equal, and bit number 2 is equal, and what? Bit number 1 is equal, and bit number 0 is equal. So this is the EQ output, right? Do you follow? Is this clear to you? Guys, I need feedback here.
You mean, Doctor, 4 bits will be the
Yeah, the equality here, the equal here is the output of the comparator here. Okay, EQ is the output of the comparator. EI is an internal signal inside the comparator. Okay, so we define it to simplify our definition of EQ now. Okay, instead of writing A3 X NOR to the B3 and it with and so on.
Okay.
Yeah, so I just used an internal function, okay, to define the XNOR of A and B, the bit number I of A and B, okay, and then used it here, okay. So if I define, so this is, let's define, okay, EI, then EQ is this, okay. Do you see that? Okay, so it's basically, I have to make sure that bit number 3 are equal, and bits number 2 are equal, and bits number 1 are equal, and bits number 0 are equal. Okay. All right. Now coming back here. So this is basically the equal operation. For the greater than now. For the greater than, pay attention, please, because it's a little bit more involved. Okay, it's simple, but it's more involved. So first of all, if you are comparing two numbers, okay, you start, the most logical way is to start from the most significant bit. Okay, and if the most significant bit of A is greater than the most significant bit of B, regardless of the rest of the number, then you know that A is greater than B. This is even in decimal. So in decimal, if you have, for example, 973 and then 199, okay, you start comparing exactly here just by looking at the 9 and the 1 here. You know that this number is greater than this number without even looking at these these digits. Do you see that? So it's the same in binary. So if you have 1000 with 0111, okay, the most significant bit of A is greater than the most significant bit of B, then you don't need to continue comparison here. You immediately know that A is greater than B just from looking at the most significant bit. Do you follow?
Yes.
Okay.
Clear. Yes.
Okay, so now what happens if this is not the case? If the most significant bit is indeed equal. So if we say 0 and then let's say 1 0 0 and then 0 and then 0 1 1. Okay, so what do we do in this case? If these are equal and this is greater than this, okay, this is greater than this, then you immediately know. Again, here you don't need to check. You only need to check this part of the of A and B. Now you don't need to continue here. Okay. So here, because this is equal, we need to check the next significant bit. Okay, the next significant bit. Similarly, if these two are equal, then we check the next significant bit. Okay, but provided that all are equal before. If these are equal, all of them are equal, then we check this bit, the least significant bit. So this is the way to do it here. So we start with comparing the most significant bits together, and then if this fails, then we say if E3 is true, okay, this is an OR gate. This is an OR operation. If E3 is true, which means that A3 equals B3 and A2 is greater than B2. Do you see that? So now previously we compared the most significant bit. Now we compare the next most significant bit. Okay. If this is false as well, then we compare. We have to make sure that A3 and B3 as well as A2 and B2 are equal. Okay, and then we compare if A1, or we check if A1 is greater than B1. Okay, if all fails, then we have to make sure that this is the case here. If all are equal, They don't have to be zeros. They can be ones as well. Okay, they're equal. That's the most important thing. And A0 is greater than B0, then GT will be 1. Okay, so GT, which is A greater than B, will be 1 if in either one of these cases. So my GT signal will be, how do I check for greater than, by the way? At the bit level, I can show you here a little. So if I have AI and BI, okay, and I have the signal AI greater than BI. Okay, what are the possibilities in binary? It is simple. I have 4 possibilities: 0, 1, 0, 1, and 0, 0, 1, 1. Okay, now for each case, I report the value of AI greater than BI, and then derive a logical expression for this. Okay, so here it is false. Okay, the second row it is false, third row it is true, and then it is false. So I know that this is nothing but min-term number 2, which is AI ended with BI complement. Okay, so I need to have AI as 1 and BI as 0 in order for the greater than to be true. Okay. All right, so this is why I'm using this expression here. Okay, so A2 is greater than B2 is A2 B2 complement, can be replaced with that, and A1 greater than B1 is A1 B1 complement, and so on and so forth. So my GT signal is going to be A3 B3 complement, which is nothing but the result of this expression here, or with E3. What is E3? Who can tell me what is the value of E3? How can we derive it from A and B? Anyone? This E3, what does it equal to? This E3 here.
A3 XNORed with B3.
Excellent. Yeah. So just keep this in mind, please. Okay. So this will tell me that A3 and B3 are equal, and then I check for the greater than for bit number 2 here. Okay. And if both position 3 and 2 are equal, then I check for position 1 for greater than. And similarly for the last one, if the first 3 positions, the most significant 3 positions are equal, I check for greater than in the least significant bit. Okay. All right. Now I don't have to explain less than because it's going to be the same. Okay. It's going to be the same, except that you need to replace greater than with less than. Okay. And derive an expression for less than. Who can tell me AI less than BI is equivalent to in Boolean algebra? Like this expression here. It's going to be, in order for AI less than BI to be true, you have to have in Boolean algebra AI being 0 and BI being 1. So it is AI complement now ended with BI. Okay. So this is the expression for less than. You can derive it in the same exact way. Also, another way of deriving it is using the 2 signals greater than and equal. You basically take the NOR of them, okay, in order to calculate the less than. You don't have to calculate it using this expression here. You can calculate it using this expression. However, you have to calculate GT using this expression, okay, and EQ using this expression, and then you can calculate LT using this expression. Anyone doesn't see why we can do LT using this expression? It's basically because if you invert the greater than or equal to, okay, if you invert it, then you get a less than, okay? And you can see that this design is much more manageable than basically a 256 rows truth table, okay, which will lead us to a 256, actually three 256 K maps, 3 to 56 cells K maps, okay, which is intractable for a pen and paper, pen and paper exercise, but you can do it using a computer anyway. Okay, next time we will discuss another way of doing this using iterative design, okay? Just like the way we did the ripple carry adder. The ripple carry adder, we designed the full adder, okay? And then used the same cell again and again and again, okay? So next time we will see a way to design a comparator, okay, using iterative design as well. So you'll have to develop a bit comparator first, okay, a bit slice of the comparator, and then replicate it for every bit from either the least significant bit to the most significant bit, or the most significant bit to the least significant bit. But what is inside is going to be different for the two versions, okay? All right. I'm going to stop recording now, and we'll discuss this iterative design of the comparator next time, inshallah.